Oh, I'm streaming. Never mind. Never mind, it's working. So what we're gonna do today is very simple. Last time we looked at how to that's music. How to oh my god, where is it? Stream manager. There we are. How to implement binary addition and stuff like that. And while it's useful to know how it works and why, I think it's even more useful to actually go through the steps of doing it. So one thing that I mentioned is, as an exercise, you should probably try to implement number with base 4 and 4 symbols. And you do that by hand, and it's fine and handy. It takes a bit, but it's not too hard. It's just manual work. However, the good thing about programming is, well, you do the thing once, and then it's done forever for everyone. So that's what we're going to do now. We're going to implement binary addition as we've seen it before, by doing like adding 2 things and then having a carry, and adding 3 things and then adding a carry and then adding 3 things. And we're going to also keep the behavior that we've seen. That is, if you have 4-digit numbers added together, you get a 4-digit number. That is wrapping around if you run over the limit. Okay, let's get started with the Xcode playground. I'm gonna call this binary addition. So you remember the scale that I drawn about where every topic fits? Is it dying? It's fine. So on one end, sorry, you had like hardware, circuits, assembly, etc. On the other hand, you had formal verification, theorems, dependent type theory. In the middle, we have all the range of programming with different types, with different languages. And now we're right in the middle because we are implementing. Oh, where's this thing about? We're implementing in a general purpose programming language something that comes from hardware. I don't remember which side is which, but from the middle we're going to one side, and we're also going to the other side by using it in Idris and implementing groups. All right, let's get started. The font is a bit small. Can we make it bigger? Yes. I think that's perfect. So what do we need to know? We need to know the base that we're using. So we're going to use binaries. For this, I'm going to make an enum binary. It has 2 cases, has 0, it has 1. Okay. Now what we need to know is how do we add 2 binary numbers together. So I'm going to use the representation that if you have 2 inputs, you will get 2 outputs, 1 for the carry and 1 for the value. So binary func binary add. Also, I'm using Swift here because I like Swift. It's really nice. Swift playgrounds are really nice. It's really easy, I think, to learn. It's really easy and fun to use. And I think a lot of people are not very, they don't like it very much. And I want to change that. So I'm using Swift. So you have 2 inputs. So you have left input, which is a binary number. You have the right input, which is a binary number. And that gives you 2 binary numbers. And we're going to use the convention that the first one is the value and the second one is the carry. And we could make a struct for this, I don't care. I'll do that some other day. So, given those 2, let's switch. Let's use a switch. switches are really nice. So we're going to switch on both the left side and the right side. And so if we get 0 and 0, why did I capitalize this? I mean, I know I capitalized this, but you're not supposed to capitalize those. At least not in Swift. So if we get 0 and 0, the return 0 plus 0 is 0. So there we go. Now the other cases are 1 and 1. If you get 1 and 1, that's 2. The problem is 1 and 1. Which one is the carry and which one is the value? I know what I'm going to do this struct. Struct, I'm going to call this carry bit, carry binary. It's going to have a value. It's going to have a carry. And this is carry binary. Carry binary, value is 0, carry 0. All right, for 1 and 1, the value is 0, but the carry is 1, right? Because the first value is like because of this. Because 1 plus 1 equal 2 in decimal equal 10 in binary. And since the rightmost, since the rightmost digit is the value, then the carry must be 1. The carry is the one that's at 1. And the last two cases are 0 and 1, and 1 and 0. And in this case, we just return 1, which means carry, which means the value is 1, and the carry is 0. And we can remove the default case because our switch is exhaustive. Does it compile? Looks like it does. Yeah, I forgot to advertise this on social media, so let me do that very quickly. And we are live. Okay. That's the simple adding two things together. But remember, if I want to add 1001 and 1100, I need to add 3 numbers together, right? Because that's a bad example. Let's go with this one. Oh, that's also a bad example. Yeah, that's a good example. Right, if I add the last 2 numbers here, 1 and 1, that's 10. So the first digit, the second digit is 0, and first digit is 1. So you have 1 as carry. And then here, this column here, you need to add 3 numbers together. You need to add 1, 1, 1, and 1, 1, 1 is 3. Which is 1 and 1. And then you need to add 2 numbers together, but 2 of them are 0. So 1 plus 0, 0 is 1. And then 1 plus 1 is 1 plus 0 is 1. And that's the result. So you need to add 3 numbers together. So binary add is not enough. What we need is func full add. And we're going to call this I'm going to call this first like F like first, S like second, and T like third, And we're going to also return a carry binary. And I'm not going to implement this right now. Or do I? No, let's do it. Let's do it. So if we look at all the cases we have 0, 0, 0, that's 0, 0, right? Or rather, plus and plus. Now you have 1 plus 0 plus 0. That's 0, 1. Then you have 1 plus 1 plus 0. That's 2, which is 10. And then you have 1 plus 1 plus 1. That's 3, 11. So again, as we've seen before, we only use one extra digit to express every possible addition. And we need to, those are permutation, we have to detect 1 and 0, 0, whatever the order of those. So let's go through there. So we're going to use the same thing. We're going to switch between every one of these and detect the pattern that we need. So 0, 0, 0. This is carry binary of 0 and 0. All right, next one. I can already remove the default because we know we're going to be exhaustive. So 1 plus 1 plus 1. This is 11, which means a value of 1 and a carry of 1. Then we have the cases where we return 2, so 10. Well, let's start with the cases where we return 1. We return 1 where there's only 1, 1. So 0, 0, 1. That returns 1, right? And 1 means a value of 1 and a carry of 0. And then you have the case where you have 1, 1, 0. And that's 2, so that returns 10. And 10 means a value of 0 and a carry of 1. But that's not it. Like there is all the permutation of 0, 0, 1 that we're missing. So I'm just going to add them here. So this is 0, this is 1. Right? And here as well. So this is 0, this is 1. And this is 0, this is 1. So you see you have 2 1s here, then we have 1 on either side, and then the 2 1s at the end. And here we have the 2 zeros at the beginning, the zeros on either side, and the zeros at the end. And if I compile this, it should be exhaustive, which means we have taken care of all the cases. And it's not complaining, so I guess it's correct. All right, next thing. We need to add binary numbers. But the problem is, well, if I go back here, this is not a binary number. Well, rather, this is a binary number, but we don't have a way to represent them. So what we're going to do is we're going to represent them as arrays of bits, so arrays of binary. And arrays are written with a bracket, as is customary. And the trick is we need to return an array that is the same size as the other array. I'm going to drink here because I'm going to lose my voice if I don't. Okay, how do we check that two arrays are the same? Well, I don't know, so I'm not going to think about this. I'm just going to say loop over all the pairs of the first one of the first array and the first one of the second array. And for this, I'm going to zip left and right together. So zip takes an array of things, another array of things, and like pairs up each element one by one, saying, well, I have this element here and I have this element here, they should be together. And I have this element here and this element here, should be together. And keep going with all the elements. And if you have one element too much, like for example, here I have 3 and here I have 5, it's gonna zip the first one, the first 2s, the first 3, and then gonna drop the extra 2. So you end up with only 3 elements. So that ensures that both are arrays at the same size. But if they're not, nothing happens, which is good and bad. In our case, we don't really care. It's fine. And there is something else that we need to do is we need to put the result somewhere. And the result will be in an accumulator. And we're going to return the accumulator at the end. The last thing we need is we need a carry. So the carry is going to be 0 at the beginning, because when you do that, you remember this addition, it's like you have a carry of 0 here. It's the same thing. We're gonna use the same logic for every element when we start at the beginning and then keep going. So that's a binary. So how do we compute this thing? So this thing is the value of the sum of those 3 numbers. So we're going to sum the first 3 numbers. And for this, well, we're going to do add a full add of the first element of the left one, then second element, first element of the second one, and then the carry. Right, and that's our sum. That's our result between the carry and the value. And now we're going to say accumulator dot what is it? Push? No, is it append? It is append of sum dot value. Then we're going to say the old carry is the new carry. There we go. And that's it. Literally, that's it. That should just work. And the reason it will work is, see here, with zip, we make sure that the 2 arrays are the same length. And at the end, we return an array, but we drop the carry. We drop the extra element, which is exactly what we used to do, right? If you have 11 and you have 1 and you do plus here, well, the sum is 1 plus 1, that's 10. Well, let's do 11 plus 11. And then you add those 3, and then you have 1 here and 1 here, but we actually don't care about the extra one, so we just drop it. We drop the extra thing on the left. And here, that's what we do. We keep building up an array. But we never add the final carry. You can see at the end, I never add the final carry. If I were to add the final carry, I would do append carry. But we're not doing this. Also, you will notice this goes from left to right. But when we're doing this strategy here, we're going from right to left. So we have to be a bit careful about how we convert from one representation to the other. So let's go with this example here that we just computed. So just to make sure we're correct, 1 plus 1 is 10, 0, we have 1 here. 1 plus 1 plus 1 is 3, which is 11, so 1 plus 1 here. and 1 plus 0 is 1, and then 1 plus 0 is 1. Perfect. So to test this, we're going to do, how much is this? This is 1 plus 2 is 3, plus 0 is still 3, plus 8 is 11 in decimal, and this is 3. This at the end should be 14. Is this 14? That's 8 plus 4 plus 2. That's 8 plus 4, that's 12, plus 2, that's 14. Yeah. All right. Now, since those are in reverse order, what's the name? Oh, it's just add. We need to do 1, 1, 0, 1. So I'm doing this one, right? Let's do it this way. $11, and here we're gonna do 1, 1, 0, 0, and that's 3. That should give us that should give us 0, 1, 1, 1, right? Because this is, it's 14 reversed. All right, compile, run the result here. And there we go, 0 and 1. It's exactly what I have here. All right, so that was incredibly simple and easy, and I would argue intuitive. There is one more thing we can do is binary add. We can now rewrite this as, we can say binary add equal full add x, y, and 0. And I can do binary add of 1 and 1, and I will get, oh, come on. It's not helpful. Yeah, I know it's 0, 1, but it doesn't tell me which one is which. Come on. Okay, whatever. So 1 and 1 should be 0. Yeah, there we go. And carry should be 1. Yeah, there you go. So now we've written binary add as a full add that takes as third argument 0, right? Because if we add two numbers together, it's like we add three numbers together, but one of them is 0. And this is a lambda syntax. Okay, so we've been adding two numbers together. I'm not sure what I should do next. What time is it? Oh, we have plenty of time. Plenty of time. All right, you know what? Let's do the same thing in Idris, because I think that's what people are here for in general. Yeah, I want a new window. Oh, that's really small. I want a new window actually. Split them up. All right. I'm going to make a new directory called binary. That's really small. It's bigger. And we call our function, our file, binary.idr module binary. And I don't like it here, so I'm gonna, can I, there we go. And now we can summon Idris. And we can load binary. Okay, so let's do the same thing, but in Idris this time. I'm going to change just one thing. So you remember how we weren't sure that the two lengths were correct. So here's a bug. Here's a bug. Let me show you a bug. We can fix this bug, but I'm not going to fix it because I don't care. Here's a bug. See this thing? The zeros here. If we remove them, bam, that's wrong. That's super wrong. 0, 1 is not correct. And the reason is because we have this array and zip takes the smallest size array. So it's going to truncate those two last numbers and going to do the addition 1 and 1 and 1 and 1. And 1 and 1 plus 1 and 1 is 1, 0, 1. 1, 1, 0. And so the one that is supposed to be in front here is just dropped. But it should work. Right? Oh, it's actually here. I'm bad. I'm dumb. Like, yeah, it should be 1, 1, 0, 1, 1, 1, 0. But the first two ones are being dropped, and they shouldn't. No, wait, what? 1, 1. Wait a second. Am I stupid? Just want to check if it's 1, 1, 0. Yeah, 1, 1, 0. From right to left. That's wrong. That's bad. We can fix it by adding, like, padding zeros until we get the same length in both cases. But that's too much work. I don't care enough to do this. And the reason I don't care enough is because Idris can take care of this for me. So if I say binary is equal 0 or 1, I'm going to do exactly the same thing. I'm going to do full add of A, B, C binary. And I'm going to return carry binary and record carry binary where structor is make carry binary, and the two values are value binary and carry binary. All right, let's keep going. So now we need to do the same thing. We need to pattern match on the first three thing and check that we have the same thing. I have 0, 0, 0, 0, 0 for 0, 1, 1, 1 for 1, and at least 1 or 2 ones for the others. So let's get started. We have 0. Actually, you know what? I'm gonna showcase some Idris stuff. So I'm really lazy, so I'm just gonna say Idris, figure this out. I hope it works. Oh, it's confused because of the Idris. I'm saying, come on. Is it not working? Come on. You have another instance running. Idris. Here's the one. It's not working. Are you kidding me? Do I not have it installed? Wait a second. Idris Vim, it's here. Yeah, I don't understand why it's not working. No such viable binary. That is strange. No type declaration of binary. Date. What? I'm so confused. Why is it complaining? Is my record wrong? I think my record is wrong. Idris record syntax. Record. Yeah, that should work. That should work. I'm so confused. Oh my god. There we go, okay. Alright, so I'm just telling the compiler, figure stuff out for me because I can't be bothered. And it's just doing it. Okay, so this is the case where we return 1 and 1. Yes, 1 and 1. This is the case where we return 0 and 0. And now here we have 1 1. Here we have 1 1. And here we have 1 1, right? Yeah. So all those return as value 1 and as carry 0. And now here those have 2 1s. So they return 0 as value and 1 as carry. Alright, I'm gonna align this because I can. And because it looks nice. Actually, I should have aligned it here instead. Yeah. Alrighty. Can I align this too? Oh my god, this is I'm falling into the ASCII art trap. Alright. Hold on. So that's the full adder. Now we need to do add of two binary things, two binary numbers, right? But binary numbers of a certain size. So here's where the magic happens. We're gonna import vectors. And vectors are like arrays or lists, except they have a fixed size and we know it in advance. So we're gonna say vect of length L of binary vect of length L of binary returns a vect of length L of binary. Right? L is the same length from the beginning to end, and we don't have to care about the case where we pass two values of different length because it's impossible. I'm just going to massage a bit this type signature. A, B, vect. There we go. And same thing, I'm not gonna write anything, I don't care. I mean, I do care, slightly. Okay, and now, oh, we need to carry. I forgot about this. So remember, if we have, yeah, I'm gonna need a carry, so I'm gonna add it here. And here's the carry, don't care. So remember, the first element of the returning array is the addition of the carry, the first element of the first array, and the first element of the second array. So it's, we're gonna do it like this. So that's the value, and that's the carry, and that is full add. I'm gonna make that next line. Full add of x, y, and c, right? And then we're going to keep going with the array and keep adding stuff together. And so then we're going to do add xs, ys, and the new carry, which is card together, and do value prepended to this. And this should work. Holes in binary add. Where's the hole? Plane 25. Is it? No. Ah, full add. Okay, that's working. And so now I take the same example, this thing, right? So that's 14. How do I do that? I just paste it. And I'm going to do sum is a vect of 4 binary, and sum is equal to full add of this one, dot g, and capitalize everything. All right. Need to give it a carry. I'm gonna do add equal a b vect l binary vect l binary add prime of a b 0. So I'm just saying add is defined in terms of add prime, and add prime is the same except it has the carry stuff. Binary carry, where is it? Oh. All right, it's working. And now if I type sum, I get 110, which is exactly the same result as here, 110. All right, now what happens if I do bad stuff, right? I'm gonna do the same thing, except we are going to remove the the zeros here, which are extra. And we get a compile error, which is really neat, because now we know that those two things cannot possibly be added together because they're not the same size. And that's the great stuff about this, is that we can't possibly make a mistake of size, because the compiler will tell you, those size don't match. And then it'll tell you, well, why? Because I'm trying to reduce things together, and I was expecting something of length 0, and I got something of length 2. So it means that it was going through this one, finished it, then went through this one and said, oh, I have 2 left over, and I already went through the other one. So what gives? So that's the first thing. And the second thing we can do is we can define a group. So remember a group. What is a group? So a group has has elements. It has elements. We're gonna symbolize it with type. It has a neutral, which is an element. It has an operation from element to element. Well, it takes 2 elements rather and returns an element. And the last thing is order doesn't matter. So if I do A, B, C, 3 elements, then I have this property. I'm going to call this up. Have A, up, B, up, C equals A, up, B, up, C. Right? I do A, B, and C, or A and B and C, and that's the same thing. Am I missing something? Oh, every element has an inverse. So given an element, I get an element, and the property that we want to check is that given an element A, then A up neutral, A up inverse A equal neutral. There we go. And maybe you're gonna find this amazing, or maybe you don't get it. But this is almost precisely legit Idris code. So if we do record group, where constructor make group, does this compile? No. Oh, because of this? No, why? It's complaining about C. Oh, because I'm putting an extra S here. Yep, that's legit Idris. So we wrote our definition as intuitively as we thought about it, and that works. So given a type, well, given an element, you have a neutral element, you have an operation between those elements, you have the associative property, you have an inverse for every element, and you have the fact that the inverse is true. There is one more thing you can change, is that you can parameterize the element here. If I'm not wrong, yeah. And there you go. So I think that's enough for today. I'm going to take a small break. Next time, I think I'm going to try to see if I can improve the group property for binary number of size 4. Because remember, binary number of size 4, they go all the way up to 15. At the 16, they wrap around and get to 0. So that's a finite group, and I should probably be able to implement that. All right, I'm gonna go to break, and I'll come back in like 10 minutes. See you in a bit.